Hello, everyone. I'm Roy Clark, Professor of Physics at the University of Michigan and co-host of Saturday Morning Physics. Today, we're going to showcase the work of two of our awesome graduate students, Ariana Bueno and Ryan Hubbard. Their presentation is sponsored by the Van Loo family, to whom we're especially grateful for their continuing support. There will be a question and answer session at the end of the presentations, so please email your questions to this address, physics@umich.edu, and that address will also be streamed during the talks. Now, there's no question that the outstanding work that's done by our graduate students is the lifeblood of the academic research enterprise. And with this in mind, I'm very pleased to introduce our first speaker, Ariana Bueno, who will tell us about her research on the physics of planetary and lunar landings. Ariana was born in Ecuador to Peruvian and Bolivian parents. She grew up in Miami and attended Florida International University, where she completed her bachelor's degree in mechanical engineering and physics. Ariana is now pursuing her doctorate in applied physics at the University of Michigan and conducts her research in the Climate and Space Sciences and Engineering Department. She was awarded a NASA O-STEM fellowship for her PhD studies and is also a Science Communications Fellow at the University of Michigan. Ariana was awarded the American Institute of Aeronautics and Astronautics Diversity Scholarship for the past 2 years and has had various leadership roles in organizations across campus to promote the increased inclusion and diversity of the STEM community, including the Society of Hispanic Professional Engineers and Puentes, a Latinx graduate student community organization. By way of some fun facts, Ariana is also an artist and loves to paint in her free time when she's not hanging out with her 2 rescue pit bulls. So welcome, Ariana. Our second speaker today is Ryan Hubbard, who's also carrying out his doctoral research in applied physics here at the U of M. And his work is aimed at a novel, non-invasive cancer treatment known as histotripsy. And Ryan will explain what that is during his talk. Ryan's a member of both the histotripsy group in the Department of Biomedical Engineering and also the CHO Immunology Lab at Michigan Medicine's Department of Surgery, where he's looking into a very interesting effect whereby the effects of the treatment using ultrasound induces an immuno response in the tissue surrounding tumors. So very, very interesting research. Ryan tells me that he has dealt with the COVID-19 quarantine by getting into some new hobbies, including drone flying, skateboarding, and building computers. And we'll hear more about that research that he's doing later. But first, Ariana, please go ahead and we'll hear from Ryan shortly.
Hi everyone, I'm here to present my research on instruments to study plume surface interactions, known as PSI, on the lunar surface. As Roy mentioned in my introduction, I just wanted to show a couple pictures that tell you a little bit more about me also. So just including some of those things he mentioned, some internships, my outreach. One of the murals I painted in my high school, and then some of the cultural things I like to do, like dancing and Peru and all that great stuff. So just so you get to know me a little bit more besides my research. And then with that, I do want to talk about what inspires me to do this work and this research. When I was little, I didn't think I would want to be an astronaut. It was something I learned later on in my career. With internships, I learned about the space program at Lockheed Martin, and from there, I fell in love. Space is extremely challenging, but it's also very unique. There's a lot of questions still unanswered, so I was very captivated by the unknown and doing research there. And it's very interdisciplinary, which helps a lot with my different experiences and creativity that I really enjoy to do. So I am very passionate and motivated about this subject, and I hope to introduce new things to you and that you get excited about space as well. So with that being said, I want to start off talking about the Artemis program. It's NASA's new program to return back to the moon, projected at 2024 for the first landing. And I want to talk about the goals that the Artemis program wants to achieve. So with going back to the moon, they want to be able to perform science investigations on the lunar surface. They want to develop and deliver technologies to enable human and robotic exploration. And with this, we will be able to understand more about our universe and our home planet. And we could also gain experience with interplanetary trips in space, which will allow us to maybe in the future go to Mars and other things like visit asteroids and all that cool stuff. So going to the moon involves a very big aspect, which is landing on the moon successfully, and there's a lot of risk when we do this. And this is where my research really focuses on, is understanding this specific interaction during the process of landing, figuring out what are the risks and studying this to ensure that nothing bad happens when we return to the moon. So with that, I want to show a video of the previous Apollo landing, Apollo 11 specifically. And with this, I just want you to have a clear picture of what this landing means if you haven't seen it. And I just want you to kind of focus on what that rocket exhaust plume looks like, and that's something I'll be talking about.
5.5 pounds. 6.5 pounds. 5.5 pounds. 9 forward. Good. 620 feet. 100 feet. 3.5 down. 9 forward. 5%. 75. 75 feet. That's looking good. Down a half. 6 forward. 60 seconds. Lights on. 6. Down 2.5. Forward.
All right, so I know that's a short clip, but I just wanted you to see that process of it landing. And then you can, so at the end you saw that it focused in on the rocket exhaust plume, and you could actually see some particles being ejected. So I just wanted you to keep that in mind and paint a picture in your head of what I'm talking about. So with that, I want to give a definition of what plume surface interaction is. I've been saying PSI, I've been talking about it, but maybe you don't really quite understand yet what it means. So I like to explain this with a simple equation. We have regolith. So regolith is the loose layer of material that it incorporates dust, sand, gravel, whatever's made up the surface. So it could also be, for example, Mars, regolith on Mars, or regolith on the moon, or even there's regolith here on Earth. So that regolith on the moon interacts with the rocket exhaust plume, as you saw in the previous video. And with that, you get this interaction that we call plume surface interaction. And this can, again, result in a lot of dangerous things and risk to future lunar missions. So with that, I want to give another example, but actually with more of a current event. So if you haven't heard, we've sent a new rover to Mars called Perseverance, and we actually just got some footage of it landing, which is really awesome. And this gives a good example of what this PSI, this plume surface interaction, looks like on the surface of Mars.
100 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the.
Okay, so before they start yelling with excitement, I'll stop that video. But with that video, you can see how that interaction looks on the surface of Mars. And I just wanted to include this because it's another application of this research. We're not just focusing on the moon, we could also apply this to different things like Mars and asteroids and other planetary bodies that we decide to investigate. So what that showed you was that interaction. You saw a lot of dust in the air, and you even saw pretty large particles or rocks being shot out as well. So that gives a clearer picture, I think, of what plume surface interaction is.
We are starting.
And then with that, I want to talk a little bit about the motivation. So why do we care about this interaction? Why is PSI so important? And like I mentioned, it does pose a lot of risk to the mission. So we need to understand it in order to ensure that we land safely, especially when we're dealing with astronauts and humans. We want to make sure that they land safely. And then with that too, we want to make sure that our hardware and our spacecraft and the instrumentation is protected during this process. And then we also want to be able to successfully conduct scientific investigations. So this is one of the biggest goals of the Artemis program. And to do that, we need to make sure that the surface isn't contaminated by all this dust and rock. So with that, we want to understand and quantify the PSI effects and develop mitigation strategies to ensure that this doesn't happen in the future. And with that process, we'll gain knowledge about the surface of the moon, which is an additional plus. And we can also provide data to help advance dust mitigation technologies. And I'll talk a little bit more about dust mitigation later on. So again, I just want to recap what I've discussed. Rocket exhaust plumes, again, interact with the surface of the moon, and this causes an alteration of the physical state of the landing site, so everything around the lunar lander once it lands. And this can contain potential hazards to the spacecraft. And then we also saw dust and rocks being ejected and lofted up in the atmosphere, and they could even be inserted into lunar orbit when we're looking at the moon. So there are significant gaps in knowledge in this research, and that's why this research is so important. And in order to understand more, we need to take measurements during the landing of the spacecraft, so in real time, and that's why we're developing these PSI-dedicated instruments. So with that, I want to start the demo, and I want to encourage you to feel free to try this at home. And all you need, and you can see here in this setup, is some flour and cocoa powder or different types of powder, and this will act as your dust and the finer particles. And then you can use rice or sprinkles to act as larger particles or rocks. You'll poke a hole, so you can use this water bottle, poke a hole on the top, and it's going to be empty. And then this you'll use to squeeze out, and it'll act as like your lander and the plume. Or you can even use a duster that you use to like clean keyboards, and this does a pretty good job as well. So now I want to ask Monica to help me out with the demo, and we'll see this interaction in using household items. Awesome. Okay, thank you. So hopefully with that, you got a really good image of what that dust looks like, right? So there's a lot of dust in the air, and you could also even see some of the rice, which were dyed green, how they've been ejected outwards, right? So how they're now all over the place. And you can also see the flour that was the underneath layer now above, right? It's exposed. So that just gives you, I think, a really cool demonstration of what this interaction looks like. And with that, I want to move on to talk about the risks. So I've been talking about the dangers, the risks, so what exactly are these risks? And I've mentioned a couple of them. So like I mentioned, the high-speed particles can damage the spacecraft upon impact or even surrounding hardware. The spread of dust can contaminate the surface science. Dust can even be inserted into the lunar orbit, and that can hurt like other things like orbiters that are going around the moon or other hardware that's in orbit. It can limit visibility. As you saw in the Mars Perseverance video, there was a lot of dust upon landing, and the camera couldn't even see anything. So this obviously becomes a problem if you're an astronaut steering and trying to land on the surface. Destabilization, so you can land at a tilt, which is not good. High convective heating, and it could spoof radar signals and other things. And here on the image on the left, you can see an example of the Apollo 12 mission, and this just shows like how the surface was affected by PSI. And you can even see a large rock where it's labeled A, and that was actually moved over during this process. So again, the reason why we know that this interaction is super important is because we've seen it affect missions in the past. And I wanted to give a couple of examples. So I talked about tilt requirements. The Apollo 15 lander actually landed at a 12-degree tilt, which almost led to mission failure. 12 degrees doesn't seem like a lot, but when you're landing on a place that's unknown with a lot of things that can get in the way of your spacecraft and your hardware, this is really important, and we want to avoid this. And like I mentioned, a lot of the Apollo landings suffered visibility issues with all the dust in the exosphere. There was heating problems as well in the lander struts in the Apollo 11 mission. Apollo 12 saw damage to the hardware, and then there's some examples of Mars as well. So InSight and MSL suffered damage to their camera functions and some sensor damage. So this just proves to us that we need to figure out what's happening to avoid this when we go back to the moon. And then I want to get into a little bit of the physics of PSI. So there's 3 categories: ejected dynamics, plume physics, and erosion physics. So ejected dynamics is what I've been talking to you about, those particles going up in the air at really high speeds. And then we have plume physics, which talks more about the effects of the plume gas ionization and all the stuff that can happen with heating or affecting radars. And then erosion physics talks more about the surface. So what's happening upon touchdown with contact with the surface. And this image kind of gives a little bit of that processes. So 1 can show the plume gas, 2 is showing more of that particle in the air, the erosion, and 3 can signal the radar interference, for example. So there's a lot of things we need to consider when we're doing this research. We have to consider moon's gravity, the exosphere density. As you know, the moon doesn't really have an atmosphere, so how does this affect PSI? And then the mass and thrust of the spacecraft, physical properties of the regolith itself, and this has a lot to do and depend on where we decide to land on the moon. So for example, if we decide to land on the polar regions, the soil, or not soil, but regolith has different compositions. And then the engine configuration of the different spacecraft, so if it's multi-engine, whether it decides to hover before actually landing, and the spacecraft design itself, and where we decide to mount these instruments that we're developing, or if they decide to install shields or other hardened covers that work as mitigation strategies. And here's an image, which is really awesome, of the different designs that NASA has just accepted these companies to do for their lunar landers. So this just shows like the variety of the different spacecraft design that we might be working with. So what have we learned so far? As I mentioned, the only research or the only data we've collected is from the Apollo missions, and we didn't have anything targeted specifically to this interaction. So what we learned is just based on observations, and we saw that generally there were no crater formations when we landed on the moon, and that's a little bit different than what we see in Mars, for example. And then PSI always spreads horizontally, and that's why you can see a lot of the surface being altered from like large distances outwards instead of just like vertical. And then usually the PSI, the interaction begins about 30 to 40 feet above the surface. And you saw that same thing happen in Mars. She was counting down how far and how close we were to landing, and then you can see how that interaction already started to speed up. And then we've even seen velocities of these particles reaching up to 3 kilometers per second. And to give you an idea, 2.4 kilometers per second is the escape of the lunar orbit velocity. And then Apollo landers have even been able to move rocks the size of 10 centimeters, which is pretty big. So we want to know how big the rocks can be that they move. So now I kind of want to recap what the focus of the research is again. So we want to develop capabilities to quantify this PSI effect. And that involves maturing concepts like our instruments to measure the different fundamental PSI processes, so the different physics that I talked about. And then with this, we want to advance the science to ensure, and we tell the companies what these risks are so that they can change their spacecraft design and come up with mitigation strategies, as well as helping scientists and engineers do more research on developing dust mitigation. So especially if we plan on landing multiple times on the moon, we're gonna be collecting a lot of dust over time. And we know that lunar regolith can be very hazardous and sharp, and we saw that in the Apollo missions when it damaged the astronaut suits. So we want to make sure that we can come up with ways to avoid this dust damaging in the future at everything that we have, including base or instruments on the surface of the moon. So with that, I want to summarize with a little diagram that helps me kind of put it into perspective what I'm doing. So again, our main goal is understanding PSI. And with that, we don't have data about PSI, so we need to collect that data and analyze that data. To collect the data, we're developing these instrumentations, and we need to do ground testing to ensure that it'll work once we mount it onto the lunar landers, and we need to assess the requirements. A lot of these instruments are already developed, but for different applications. So we need to assess requirements to make sure that it can work for lunar applications. And then analyze the data involves a lot of calculations depending on the parameters that we want to measure. And then running simulations. Simulations is a very large section of this research as well, and a separate team at NASA is handling that. But basically what it does is model and use prediction capabilities to see what might happen in different scenarios when landing on the moon. So I've said a lot, I've mentioned a lot of different types of research, so I just kind of want to hone it in on what I'm doing specifically for my PhD thesis. So I have 2 scientific goals here. I'm interested in learning about the long-term contamination on the moon. So that involves quantifying how much dust will be injected into the orbit, figuring out the size and different range of particles and shapes, and then electric field effects, which is a very interesting topic, and I can do a whole lecture on just that. But I did want to mention that that's something we do want to consider as well, the electric fields on the moon. And then with that, analyzing how these particles might damage, especially if they're going at really high speeds. And with that, we can measure, again, the velocity and energies, and do a lot of experimental testing to see what type of materials gets affected more by this process and other things. So with that, as a scientist, I have questions, just like you probably already have about what I've presented. So I continue to ask these things to make sure that I'm guided in the path to answer my scientific goals. So I want to know how far these ejected particles can travel, and how can it affect nearby hardware that's on the surface? How long does dust remain lofted after engine shutdown? How does PSI differ in different landing sites? And then how does lander size and engine configuration affect PSI? So these are some of the questions that guide me as I try to think about what we want to test and what we want to measure. And I'm sure that you could probably add a bunch of new ones in the Q&A as well. So what exactly will we measure? And to answer my scientific goals, I want to know the particle velocity, excuse me. I want to know the particle energy. I want to count how many times these particles impact the spacecraft. And then I want to know the size and shape of the particles. Excuse me. Okay, and then additionally, I can help to measure different things as well during this process, like how the crater, if there is any crater formation, and then also measure things about the landing base environment, including the plume itself, so the temperature and pressure of this interaction. So with that, I want to introduce the instruments that I've been talking about, and we work for this Commercial Lunar Payload Services CLPS. We're doing a proposal for it, and we're presenting this instrument suite. So we still have to select what instruments we want to include in this, but for now we have 2 instruments per category, with the additional category of dust particle characterization that also helps with dust mitigation. So I'm quickly just going to go over what these instruments do. And I just want to focus that these 4 instruments first are mainly for modeling and simulations, since they're analyzing the plume itself. So the first one will monitor the pressure and heating rate maps of that landing base environment. And then the second one can capture thermal images of the rocket plume, and this can again help us with modeling. The 2 images on the right are the ones that are showing those 2 instruments. And then we have SCALPS, which is going to capture images of the onset of PSI and regolith erosion. So it's going to be facing the actual surface and seeing how that interaction is. And then we have EjectaStorm that's measuring the plume-induced dust blowing rate. And then we have 4 instruments that are working more with my scientific goals. So we have the EFS, which is the electric field sensor, and that is measuring the charging of the lander and electrification of the dust cloud. And that's like what I was mentioning with the electric fields and its effects. And then we have DIRT, which is to measure the speed of the ejecta. We have saltation, which measures the energy. And then we have the optical microscope, which basically just captures images of the particles hitting the instrument. And on the left side, you see a picture of the electric field sensor on the top and SALT at the bottom. So I want to take just a couple minutes to talk about one specific instrument that I've been doing a lot of work on, which is a saltation sensor. So this sensor was actually first developed for Mars and to measure the energy influx of saltating particles for Mars. So what we need to do now is mature this instrument to make sure it works on the moon. And again, saltating particles have different composition and they're very different from lunar regolith particles. So we need to take this into consideration when developing and maturing this technology for the moon. And I'll roughly go over how this instrument works. So what this instrument does, it measures the particle impact count. So how many times those particles are hitting this instrument. And how it does that is uses a piezoelectric material that's really sensitive to these signals and impacts. So once we get those impact signals, we convert it into a Gaussian shaped pulse, so a little bit of math. And then we applied it against a certain threshold. And this depends again on what energy we are looking for and what we care about. So then those pulse peaks, the graph at the bottom that you see, those peaks, you can take the energy under those peaks and it will, the area under the peaks and it will give you the energy. And then we also plan on adding other types of sensors like pressure and temperature sensors to this instrument to give us a little bit more of an idea of that interaction of the particles impacting. So with that, I want to talk a little bit about testing that we're going to do. We're going to work with the NASA facilities, the Glenn Research Center and Marshall Space Flight Center. And we're going to do hot fire tests with regolith in vacuum chambers. So that image is an example of a vacuum chamber. And we have different simulates here on Earth that we can use to use as regolith on the moon. And then we're going to use flight scale and subscale. So the real life size landers and then a smaller version. And with that, I have to make sure that I scale everything correctly. So I'm helping with like scaling laws. And then we're also going to use the Johns Hopkins high velocity particle rig. And this is to ensure that our instruments will be able to work with really high speed particles. And then we can do shock and vibration testing here at U of M at the CLASP department. So then what am I doing with data analysis? I'm basically supporting everything I can with the different types of physics. So again, plume physics, ejecta dynamics, and erosion physics. And like I mentioned, this will help us validate the simulations and modeling for the plume. So what we can model is actually quite a couple of things. We can do ejecta transport, so how these particles will move, and then crater formation if there is any, erosion processes, how that surface looks and how it's affected by PSI. Heating, like I talked about, and aerodynamic effects, again, from the gas ionization. So that was a lot, and I just want to summarize with what we will gain, again, from this research. So it's really important that when I complete this, when I work on it, then we come out with a deeper understanding of PSI. And then with that, we'll have in-flight real-time data to characterize the risk of PSI during missions, and we can give these to the different companies working on spacecraft designs and give this back to NASA to ensure we have the appropriate mitigation strategies. So those mitigation strategies can include shields or landing pads, and there's a lot of different ideas for this as well. And we can advance simulation software for prediction capabilities. So all of this in turn will hopefully ensure safe landing for our future missions. And with that, I just always like to end and encourage you to be the next space explorers too. I always like to say that space is really cool and you can do a lot of different things, not just like what I'm doing. So if you're interested, please ask me questions in the Q&A, and I hope that you're at least slightly more interested in all the great things that space has to offer. So thank you again. And then, now I'll pass it on to Ryan, which is the other presenter, and he has some awesome things to tell you guys.
Hi everyone, my name is Ryan. I work in the Historypsy lab here in the Department of Biomedical Engineering with my PI, Jin Xu, and we work in close collaboration with the Department of Surgery and the CHO Immunology Group. And today we're going to be talking about using ultrasound pulses to destroy cancer cells. So let's start at the basics. Sound waves are longitudinal waves, and they are alternating compression and expansion. And so if you look here on the figure in the bottom, you can see that when it moves through a medium, you get alternating regions of where everything's squeezed together and then it's pulled apart. And that moves through the medium. And usually when we think of sound, we're thinking of things in the hearing range. But that's only a very, very tiny fraction of the actual sound range. And so ultrasound is the region above human hearing, and it can be used for a variety of applications, but we're mostly focused on the range that is not quite as high frequency as medical imaging, and we're focusing on more destructive applications here. So, like all waves, sound waves also have the capability of interfering. And basically, interference means that when waves come into contact with each other, they can either combine to make a stronger wave, or sometimes they kind of detract from each other and cancel each other out. So I have a demo over here. And basically, what we have is we're going to have a speaker underneath this plate, and then I have a bunch of sugar that we just have strewn about. And this is going to be a good illustration of how sound has the alternating high pressure regions and low pressure regions. So if I turn on the speaker, you'll see all the sand begin to settle, and it's settling in the areas where there is a negative pressure, and the parts that evacuate the sand, that's where the pressure is positive, and it's basically throwing all the sand away. So if I change it to another frequency, let's see here. So I'm going to change it to a higher frequency, and you can see all. So now we have a different frequency, and the negative forms of the pressure wave are in different spots. And so you see where the sand is collecting. All right, so more specifically, so we talked about the basics of sound, but what is histotripsy exactly? So histotripsy is a form of ultrasound therapy that's non-invasive, and we used focused ultrasound pulses. So remember, I was talking about constructive interference. So that means that we aim all of our ultrasound pulses at a very, very tightly focused spot so that they all combine in a very, very small region and give you a very, very extreme pressure region. And so we have focused ultrasound pulses, and these are very, very short, and that's important to get the phenomenon we want to generate. So they're very short, and they're very intense. And by combining these very short, very intense sound waves, we can generate a phenomenon called acoustic cavitation. And basically, we get a really, really intense negative pressure region, and it, like in the word cavitation, it generates a cavity. And when that cavity is quickly generated, it collapses down quite violently. And this repeated process works to fractionate the tissue. And so usually when we talk about ultrasound, and we were thinking about, imaging babies, maybe some sort of sports injury, and that's not really what we're worried about in our research. Instead of imaging, we're not trying to diagnose anything, we're trying to destroy any deleterious tissue that may exist. And so imaging, you see high frequencies, 2 to 15 megahertz. That's based on sending out an ultrasound wave, waiting for a reflection, and then constructing an image. When we do histotripsy, we focus our sound pulses down, and we generate that cavitation. And wherever that cavitation occurs, those cells are going to be destroyed. So to kind of put it in context with some other types of anti-tumor therapies, you have radiofrequency ablation, which has been around for quite a bit longer. It's where the clinician will insert a needle with electrodes into the target region, and then they'll pass a current through it, and that will basically cook the tissue. It'll raise the temperature significantly. Once it gets above 50 degrees Celsius, the cells start dying pretty much spontaneously. And this, causes the tissue to start to necrose. Similar concept, or end goal, I should say, with thermal focused ultrasound. So histotripsy is a mechanical modality for destroying tissue. Thermal focused ultrasound, sometimes referred to as HIFU, is a thermal-based therapeutic ultrasound technique, where once again, they do focus down those sound waves, but they use long pulses, and the mechanism is based on absorbing the sound waves and converting that sound wave into heat. We just want to shred it up kind of like a blender. We want to generate that cavity, collapse it down, destroy it. When scientists use thermal ultrasound, it's about generating heat and cooking the tissue. And then I'm sure most people are aware of radiation therapy, so using X-rays to destroy the DNA within the tumor, and that basically stops it from proliferating. So what makes histotripsy unique is that when we generate cavitation, all of our damage, all of that destruction is specifically confined to where the cavitation cloud travels. So we get these very, very highly demarcated lesions, and it leaves behind just this, puree of, if you're treating a tumor, it's this tumor puree. If it's a blood clot, you have, this broken down blood clot, and this homogenate is then later, reabsorbed by the body naturally as it gets rid of the leftovers. And I have a video here to kind of show you what histotripsy looks like in some in vivo tissue. So it might be hard to see, but I have a little circle here to mark where the cavitation cloud is, and you might be able to see a little flickering, and that's actually the cavitation cloud moving through the tissue. And that dark region in the center, that's where the cavitation has already destroyed the tissue, and it's just leaving this soup. And so we think that soup has some really nice properties, and I'll talk about that later. But as you can see, it's all the destruction is confined specifically to where that bubble cloud is being dragged through the tissue. So there are a lot of applications or potential applications for histotripsy. The big one is obviously tumor ablation. That's what we tend to do most of our research on. But there's also been research done with deep vein thrombosis, getting rid of blood clots, intracerebral hemorrhage, ovarian cysts, benign growths like BPH, and a particular interest of mine is immunostimulation, which has become a new development with our lab. So let's talk about immunostimulation. So first, I should talk about this process called immunogenic cell death. And this is our body's primary, tool to address any spontaneously arising cancer. So at any moment, you could have, some tumor cells begin to appear in your body, and your immune system has to have a way of swiftly eliminating that. And to do this, your immune system basically needs two main ingredients. So the first one is a tumor antigen, which is basically like a signature. It's like a fingerprint, so that your body knows exactly what to eradicate, what to attack. And then it needs something called a damage-associated molecular pattern, which is basically like an alarm bell in your body that's like, oh, something's wrong, I need to address this, we need to move. And so with these two components, your body can mount potentially a successful immune response. And so the process kind of starts there. You have these cells that basically pick up the tumor antigens, transport them to a lymph node where they can find a T cell that can specifically recognize that signature. The T cell can then be activated, it proliferates, and then it goes out throughout the body looking for that tumor antigen. And when it finds it, it's going to kill that cell. And so that's the body's main mechanism of dealing with cancer cells. But obviously, if it was always that easy, if everything always worked out, then people would never develop cancer. And unfortunately, that's not the case. So ideally, you would stay in this first phase of elimination. Your body's able to recognize the cancer, it sends out the immune cells, and they're able to destroy it. But that's not always what happens. Sometimes, cancer cells are able to mutate, and some of these mutations are beneficial for the proliferation of the tumor cells. And so you get this kind of standstill where the body is trying to eliminate the tumor cells, but the tumor cells are adapting, and you get this kind of stalemate. Now, if the body is able to adapt faster than the tumor, then it'll move back into the elimination phase. If the tumor is able to outwit the immune system, then it gets the escape phase where the immune system is no longer sufficient, and this is when it becomes clinically detectable and you need to seek medical assistance. And that's where, we come in. So the driving hypothesis between using histotripsy to initiate an immune response is that tumors have all these mechanisms to evade immune detection and elimination, and we're hoping that by destroying the tumor cells, we're releasing tumor antigens, and we're releasing the danger signals, the DAMPs. And with those two key ingredients that histotripsy releases into the body, the immune system can then take over and eliminate the remaining cancer cells. That's the main gist. And other tumor therapies, there's been research looking into if things like HIFU, X-rays, and radiofrequency can also generate these kind of components. And we think the mechanical nature of histotripsy uniquely situates it because it leaves all those, after it breaks down the tumor cells, the antigens are still intact. The tumor cells are no longer viable, so they're no longer, proliferating, mutating tumor cells, but you still have that signature, so the body can pick that up and then look throughout the body for any other tumor cells it needs to eliminate. And so generally, when we do an experiment, it kind of goes something like this. So we'll have either in vitro or in vivo, we'll have a mouse, and we inject a flank tumor. We have different cell lines. Most commonly, we use a melanoma cell line. We will we'll let the tumor grow, we'll treat the tumor, and then we'll harvest it and the lymph nodes, and we'll look for, T cells, immune cells that have responded to the tumor, and we'll analyze the immune response like that. So here's our setup. So this is what it looks like in the lab. We have different types of setups for different type of applications. So this is the type of setup I use a lot. We have an ultrasound monitor, so we can monitor the cavitation cloud and see where it's moving. We have a water tank. All our experiments are done in water. We have a little micro positioner to move our transducer. On the right there, that's what a histotripsy transducer actually looks like. Each of those little circular or cylinder things are an ultrasound element. So they each emit an ultrasound pulse, and you see they're all focused at a common point, and that's so that all those sound waves can constructively interfere and generate the cavitation cloud. And so we've seen some promising results with our experiments. We've done experiments where we inoculate the tumor, we let it grow, then we treat it, and in the figure there, I'm showing the amount of CD8 infiltrating T cells. So the CD8 T cells are basically the workhorse of the anti-tumor immune response. And so if we see a high concentration of CD8 T cells, we know that the body is fighting back. And so as you see, as time goes on, so day 3, between mice that were treated and mice that weren't treated, there's a slight difference, but on day 10, there's a quite substantial difference in the infiltrating T cell populations for mice that received treatment. And that's what we like to see. We like to see that we're strongly promoting anti-tumor immune response. And so another thing that we think is promising for the histotripsy-induced immune response is that not only are we recruiting T cells into the treated tumor, we're recruiting T cells that are specifically designed to hunt tumor cells. So GP33 and GP100 are the type of antigens on our cell line that we use. And when we look at the infiltrating lymphocytes, we find that they have receptors for these specific antigens. So not only do we have an immune response, it's an immune response that's specific for the tumor cells. The immune response, we would expect to see it in the tumor that we treated because we're releasing all those danger signals, we're releasing all those antigens locally in the tumor. And so it's really good that we see them locally, but an even better response is if we can get it throughout the entire body, because in real life, you may have just one primary tumor, but you might also have metastases, and it's hard to, singly address each individual tumor. But what we've seen in research is if we have an experiment like in the figure on the right where we have a mouse, we inject 2 tumors, one on each flank, but we only treat one of the tumors, we see a significant immune response in the tumor that wasn't even treated, wasn't even touched. And so that's just a testament to the fact that the immune response, the T cells that are being activated, move through the entire body and they attack that specific antigen wherever they find it. So you can see the abscopal response is basically an untreated tumor, and it's almost as strong as a response in the actually treated tumor. And then we did another type of experiment where we had a flank tumor that we treated, but we also induced metastases in the lung. And you can see that striking figure right there where mice that received treatment, their lungs are significantly clearer than the mice that didn't receive treatment. And that's just another illustration of the tumor, of the T cells basically moving throughout the entire system and addressing the tumor cells where they find them. Okay, so here we did an experiment where we were looking at the release of HMGB1. So HMGB1 is basically a protein that naturally is found in the cells, but when the cell undergoes any type of stress, it's released into the extracellular space and it galvanizes the immune system. It's an example of a danger signal. It's a DAMP. And basically, if we see a higher concentration of HMGB1 or DAMPs, we know that that's a key component of eliciting an immune response. And so histotripsy-treated mice are exhibiting stronger concentration of HMGB1, which indicates that histotripsy is indeed generating an immunogenic cell death pathway. All right, and then so we did some experiments where we compared histotripsies to some of the other modalities that I talked about earlier. So XRT is X-ray therapy, RFA is radiofrequency, and then control is just they didn't receive any treatment. And here we're seeing that histotripsy is outshining the other techniques in terms of the percentage of tumor-infiltrating lymphocytes that are CD8 cells. So the CD8 cells, like I said before, are the workhorse of the anti-tumor immune response. So when we isolate the tumor and we look at all the lymphocytes that have migrated to that tumor, you see a higher proportion of those are the cytotoxic T cells. And then on the right, I have the secondary tumor, which is the abscopal, the untreated tumor. And you see that histotripsy has a stronger systemic response as well. And so next I want to talk about checkpoint inhibitors. So checkpoint inhibitors have been a really big breakthrough in immunology in the last couple years. I think a couple years ago, the inventors actually received the Nobel Prize in medicine. And basically, T cells have an on switch and an off switch. So the on switch is a receptor called CD28 that galvanizes the T cell, tells it needs to activate, proliferate, and go address some need in the body. That's good when we're talking about a tumor cell, but your T cells naturally possess receptors that tell it to switch off, and this helps prevent autoimmunity. It lets your T cells know that the fight has been won, you can calm down now. And these are called checkpoint proteins. And tumors have this very insidious mechanism where they can prematurely activate the checkpoint proteins and turn the T cell off, and then it's not eradicating the tumor anymore. And obviously that's not good. So checkpoint inhibitors are basically these drugs that block the off switch on your T cell so that it stays engaged longer and it keeps fighting the tumor cells. And so how can we combine this with histotripsy? Well, checkpoint inhibitors aren't very effective in tumors that are non-immunogenic. So what that means is if the tumor is already able to evade the immune response, keeping those T cells engaged longer isn't effective because they're never recruited in the first place, perhaps, or they're having difficulty detect the tumor. But if we can make a tumor more immunogenic by destroying it, releasing the antigens, releasing the DAMPs, then the hypothesis is the checkpoint inhibitors will be much more effective. And so what we do is we will, in our experiments, we inoculate a tumor, we will let it grow, we'll treat it with histotripsy, And then we'll combine it with the checkpoint inhibition therapy to see if we can enhance the efficacy of that checkpoint inhibition. So here we have some tumor growth curves, basically charting the tumor growth in lab mice. And we have 4 groups, basically no treatment at all. We just gave them histotripsy. We just gave them the checkpoint inhibition, or we gave them the combination of both. And as you can see, we have 2 different tumor cell lines that we tested in it. And melanoma is a relatively immunogenic cancer, so we expect checkpoint inhibitors to work well with it. But liver tumors, the HEPA-1/6, is not an immunogenic, or it's much less immunogenic. And so this is kind of the goal. We want to make the non-immunogenic cancers more susceptible to checkpoint inhibition. And as you can see, out of all the groups that receive both histotripsy and checkpoint inhibition tend to have the most subdued tumor growth. And so that was a good sight to see. Yeah, this is the work we've been working on. It's a huge collaboration. I would like to thank all our groups that have contributed to this research, especially my advisors, Professor Xu and Dr. Cho in the immunology lab. And yeah, thank you for your time and continue my talk.
Well, thank you, Ariana and Ryan, for those great presentations. We hope you all enjoyed those those beautiful examples of the outstanding research that our graduate students are working on, illustrating the broader impacts of physics in society, in this case for space exploration and cancer therapy applications. Before we get before we get started on the questions, I want to acknowledge that Saturday Morning Physics is extremely grateful to our donors, including the Van Loo family, who sponsored today's presentations. And if you would like to inquire about making a donation to help support the program in the coming year and beyond, please send an email to physics@umich.edu. That's the same address that you're using for transmitting your questions. And we'll explain the different ways that you can do that. And we'd be very grateful to receive those emails. So we have a whole bunch of really great questions from our audience. So let's get to those. And they're really an interesting set of questions, which reflect the impact of the research that's been described. I think the way that I'd like to do this is to go in order with questions for Ariana first, and then get to the ones that relate to Ryan's talk. So if that's okay with you, Ariana, let's go ahead with some questions on a fascinating talk that you gave. So the first question is related to the exhaust plumes impact on the regolith or the ground. And the question is it possible that would change the nature of the regolith or the local conditions at the surface, such as forming a glass? For example, if there's a silicon bearing rocks in the vicinity, could glass formation or other changes increase the danger of the hazards of a landing?
That's a great question, and I think definitely there is going to be changes to the regolith or the ground, and there's a lot of research on like the erosion physics, as I mentioned before in the presentation. I think it does depend a lot on where we decide to land for the Artemis program. There's different compositions depending on whether we land closer to the poles or we want to go back to where the Apollo missions were. But overall, like this is the whole point, that we don't have data that's going to show us what exactly is going to happen. So it's so important to do this research. But we know, for example, that the lunar regolith is mainly made up of lunar breccia, which is like rock components and debris and melts that were created by like meteorite impacts. And those have different compositions that include like silicone and oxygen, aluminum, all these different elements. So it could be possible to see changes in the regolith, and possibly there's already is a lot of glass formed on the surface. So how would that change when the rocket exhaust interacts with it is also something we would be very interested in knowing, especially because the regolith is jagged and sharp, and this could definitely pose like an increase in the damage of what we would see to the spacecraft or the instrument. So yes, and hopefully we'll come up with enough data to kind of tell us how this would affect it. So great question.
Well, thank you, Harna. The second question is another really great question, and it's related to some possible application down here on Earth, and that is, could the results of your studies help to keep dust off solar panels and to extend their useful life? And this is definitely an issue because a lot of those panels are located in very dusty areas, for example, in desert regions where there's a lot of sun. So is there a kind of spin-off effect that you can imagine in the future?
Yeah, that's also a great question. And I think definitely there is an opportunity to incorporate and find different applications for this, especially when we are looking into dust mitigation solutions. So it's not only just like studying how dust is going to behave on the moon, but it's how to avoid even getting on solar panels on the moon as well. So if we come up with like different forms of shields using certain materials that dust might not be able to latch onto as easily, and this has a lot to do with the electric fields that I was talking about in the presentation as well, then we can definitely use like the results and hopefully test it here on Earth. And there also are a lot of similar dust materials here on Earth that act the same as on the moon. So we use like volcanic materials that we use as the lunar simulates when we do experiments here on Earth. So if we deal with stuff that's similar to that, then I think that definitely we can use the information that we find out in these experiments for applications here on Earth as well. So that's a really good question. I think that's also something that NASA's probably looking into and can help. And just to show you how doing research for space can help you here on Earth as well. So great question.
Yeah, it is a great question, and it kind of illustrates how when you do research using applied physics, there's always a lot of connections into other areas and disciplines, and that is the real value of doing this kind of research. I had a question, Ariana, myself actually, and that is related to an important event that's going to take place up on the surface of Mars in the next few weeks, possibly even this month. And that is, there will be the first off-planet flight. This is the 100th anniversary coming up of the Wright brothers' first flight at Kitty Hawk. And the lander was carrying a helicopter, which will be released and will hopefully take off on its first flight on another planet. And my question is, are there any special considerations that may be related to the use of rotors in an atmosphere that is very thin as regards saltation and dust effects?
Yeah, also a great question. I actually have been talking about this because it's similar effects that we've been thinking about for like the electric fields that I was mentioning. So we think that once the rotors start going and interacting with the dust, that it might actually charge up the atmosphere on Mars. So we think that we would have dust interactions, like so they would create like electric potentials, and then that could happen between the dust particles like hitting and interacting with each other, or even hitting like the blades, and that could cause like this electric potential, and then that can charge up the atmosphere. So I think that's something that is very similar to the work we're doing and for the moon as well. So it's pretty interesting that even though we don't have, again, like you mentioned, a plume, it's just a rotor, we can still have like effects on how that, like the rotor interaction and potentials that can be created by the dust interaction, which I think is very interesting. And we have instruments that can actually detect this that I mentioned. I didn't mention it in my presentation, but it's called the electric field sensor. So that one could be something that we can potentially also use on Mars as well, which is really cool. Yeah, I hope that answered the question.
Yeah, thank you very much, Ariana. And in the interest of time, I'd like to move over to Ryan's talk, for which we also received a number of interesting questions. So Ryan, if you'd like to step up to the plate, and we'll have some questions related to your work. So one question relates to the demonstration that you showed, which is sprinkling sugar grains on the surface of a vibrating plate. This is a very old technique that's used to illustrate pressure points and accumulation of particles due to variations in pressure, acoustic pressure. And by the way, that demonstration really beautifully illustrates how, in a visual way, how acoustic waves arrange themselves. So the question is that the geometry of the distribution of grains, and that means pressure points, low pressure and high pressure, is very surprising. And the arrangement of sugar grains changed drastically with frequency changing. And the question relates to that is, if you exactly doubled the frequency, in other words, go from the fundamental frequency to, which is a kind of cross-like geometry pattern, and you doubled frequency, in other words, go to the first harmonic of the initial frequency, which is known as the fundamental, what would be the results? I don't know in your demonstration if how much the frequency changed. Could you say a little bit about that, Ryan, when you changed it?
I'm not sure if I remember. I don't think I might have used like the third or fourth harmonic for the second pattern. And I think it just, it's very dependent on just how the standing waves. With the higher frequency, you'll just have more, local maxima and minima. And so that'll just give you more, regions of accumulation with the grains of sand. And it's just kind of where they stack up. Yeah,
that's right. So, so the geometry of that particular vibrating object is a little bit complicated. First of all, it's circular, So it exhibits things like drum modes, the kind of modes you get when you beat a drum. And secondly, it's anchored at the center and excited at the center with the edges free to move. So it has a very interesting set of acoustic harmonics. But without going into all those details, it's a really nice question and gets into the details of how you produce high pressure points in a technique like histotripsy. The second question related to that is in the ultrasound, pulsed ultrasound method called histotripsy, is the pulse a spectrum of frequencies, either narrowband or broadband, or is it mostly a single pure frequency? And does this influence the energy of the ultrasound wave that's used?
Yeah, generally we try and keep it as centralized on a single frequency as possible because in an ultrasound transducer, you have a ceramic piece called a piezoelectric, and to get the most sound output, you need it to resonate really well. So we try and drive it at the specific resonant frequency of the piezoelectric so that we get the most output as opposed to like a broadband driver, then we've got a lot of loss. So we want to really maximize the pressure. So we try and keep it as very, very narrowly focused in frequency as we can.
Mm-hmm. All right, good. So, so another question for Ryan. First of all, amazing work. How does this histotripsy method compare to other tumor treatments in terms of non-cancerous cell death? In other words, talking about collateral damage to surrounding tissue. Is this treatment more or less precise than some of the other treatments?
Yeah, I guess what we kind of like to brag about histotripsy is that you don't have a lot of like with radiation therapy, you have entrance and exit dose as the photons, are traveling through the body towards their treatment destination. They also, they interact with all the tissue that they travel through going up to the treatment point and coming back out the other side. And with thermal therapies, you also have like a gradient, a fall off with like the thermal dose you deliver. And so you treat like your desired region, but the regions around it also will warm up a little bit. So there might be some destruction, surrounding where you target. But with histotripsy, the only places that you're going to destroy cells are where the cavitation cloud occurs. So as long as you don't have any aberrations, which, it's not perfect. So we do have to deal with things like aberrations and attenuations. But as long as you, you have there's only cavitation where you are aiming the cavitation, then that's the only place that should have destruction. There shouldn't be collateral damage.
All right, thanks, Ryan. Another really interesting question. The immunotherapy and checkpoint inhibitor benefits are great news for histotripsy. What does industry need to see before there's a widespread adoption? Not only FDA approvals, but also physician acceptance to this new modality. So what's the regulatory status of this technique? Could you say a few words about that, Ryan?
Yeah. So just in 2019, they did the first clinical trial for histotripsy in Barcelona. They had a handful of patients. They were targeting liver tumors, and they were doing, ablation regions on the order of like 2 to 3 centimeters. And they had really good results. Everyone had a good response to it. It was just like a first in person type of trial. And I guess a lot of the hurdles for getting this into the clinic are things like, how are you going to monitor the dose? So you need some way to like, measure, are you treating where you think you're treating, and like just a metric to know just how much you're breaking down that tumor. And so there are people who work on things like sensors for cavitation so that we can like quantify, how much destruction we're actually delivering to the to the target region. And then there's a lot of things where like depending on the application, each application has like a different, transducer geometry, a different, kind of approach, because ultrasound can't travel through like lungs and bowels and bones and things like that. So, for each, so a liver tumor is going to have a different, regulation hurdle versus, like treating a tumor in the brain. And so, but it is slowly moving into the clinic.
Mm-hmm. Are there any kind of clinical estimates of when this might be widely implemented after the trials, some of the trials are completed?
I'm not sure. It
Time scale?
feels like it's very, very preclinical right now. Like in terms of like combining it with checkpoint inhibitors, I don't think there's anything like super pressing in the next couple of years. But right now they're just doing like basic clinical trials, just showing that we can ablate the tumor and that there's a good, response by the patient, things like that.
Okay. So one other question. Could you comment, Ryan, on the ability of ultrasound to break physical bonds versus chemical bonds? So I guess talking about really the difference between larger scale effects and microscopic effects on the chemical bonds.
Yeah, that's a
Good comment on that. It's a really interesting question.
I guess normally we kind of think of it in terms of like breaking physical bonds because the cavitation cloud's on the order of millimeters. And so we can like see under a microscope, we can see like the cell being shredded up. We can see like we can even like see like we have some images where like at the boundary of the tumor region, there's like a cell that's like half completely shredded and half still intact. In terms of breaking chemical bonds, I'm not really sure. It's mostly a mechanical change, a physical change where we're just, the pressure is crushing and ripping apart. To detect physical or chemical bond breaking, I would think it's not quite on a microscopic scale like that. Like it keeps the proteins intact. Like we can still like measure like the proteins in the tumor and like the cells are still there.
And and presumably that helps to enhance this immuno response, which seems to be so important for this particular technique. Because go ahead.
Oh, yeah. I was just going to say, so I would think it's a primarily physical destruction as opposed to breaking chemical bonds.
Mm-hmm. Good. Well, that seems to be all of the questions from our audience, and we thank you for submitting those, and I thank you both for providing some of the answers to those questions. So before we finish, we have a few minutes left. I'd like to ask you both, maybe with Ariana first, because you brought up this, Ariana, you brought up this important comment about, or message, I would say, like get involved, be interested in follow your dreams. So could you, just from a personal point of view, could you both tell us how you got into science? What kind of turned you on with science, and how did your dreams influence that? Ariana?
Yeah, I think that's a great question. I guess like in middle school and high school, I just started to really enjoy my science and math classes a lot more. I took physics, and that's kind of what really drew me in. I liked understanding how things worked, but I also liked building things. So that's why I started with engineering when I did my bachelor's, and then I missed a little bit more of the physics, so I added physics too. I just think that science and math like gives us so many ways to answer questions all throughout our daily lives and things that we see, and it's so easy to explain and understand how things work if you really accept and respond really well to science and math, which I think is super exciting to just kind of come up with questions and be able to answer them and do experiments and all that stuff. And then I still feel like you can be very creative with it. Like I mentioned, I do like art a lot, and I can be creative with my research and my science as well. So that's something that motivated me.
Absolutely. Thank you. So, Ryan, what's your take on that question?
That's I don't know. I guess growing up, I kind of always like to be different and stand out, and people kind of have like a bad relationship with science sometimes. They feel like it's like inaccessible or it's like inhospitable. And I don't know, that kind of just, I just wanted to be the contrarian and I would be like, oh, I want to do that. If everyone, is afraid of that, I'm kind of curious.
So, on the question of accessibility, I just want to say that this is for the young people in the audience, that if you would like some advice on how to get into science, how to get involved, even if you're in high school, especially if you're in high school, how do you get involved? We will have some advice for you, and I'm sure Ariana and Ryan will be happy to answer those kind of questions from interested students who want a pathway into science. All right, so that basically concludes our program for the winter semester. It's been not an easy semester by any means, but we hope you've enjoyed the enjoyed the program that we've had online this semester. We've had some really interesting talks, and we've had a lot of audience participation and of a kind of broad spread of audience members. So we thank you for that and for your interest in Saturday morning physics. I want to say a few thank yous to people who have made this possible. One of them is my co-host, Professor Tim Chupp, from the physics department at the University of Michigan, like myself. And also Carl Cole from the Michigan Media. He's the production manager who was put on the video presentations and put them on YouTube and so on. And I also want to thank the manager of our lecture demo lab, Monica Wood, by the way, was responsible for the demonstration that was discussed a little bit earlier in the questions to do with acoustic vibrational modes. So Monica has been responsible for all of the demos that have taken place this semester, so thank you. And lastly, but not least, our communications director, Carol Raybuck, for all her help in keeping things going over the semester under fairly difficult conditions. So we look forward to seeing you all again in the fall. We'll be continuing, whether it's in person or online. We don't really know right now, but we'll be in touch. And I wish you all a great summer, and keep thinking science. And thank you again for our speakers.